Okay then, folks, might as well get started. Hello there, my name is Matt. Thank you for coming. My name is Matt. I work for JetBrains. I'm a developer advocate, and today we're going to talk about writing allocation-free code in C#. And we're going to start really with a little bit of advice, very simple advice now. It's something which I feel like is getting a bit traditional with some of the talks I'm going to give here. Because it's a simple one. Don't do it. Don't do it. This is a talk about micro-optimizations. And on the whole, you're not really going to need to do this. So generally speaking, you probably don't want to do this. You can probably ignore a lot of the things I'm going to say here, but it's very useful to know, because you're not going to need to do this until you actually do need to do this. And then, of course, the only reason you're going to be doing that is by measuring. So please, the things I'm going to point out today, they're interesting stuff. It's useful to know in and of itself. But don't just apply these things without measuring first. This is the big slide. This is my caveat, my warning, my disclaimer. You've all heard it, so we'll move on. Right. Why? Why are we talking about this? And what's so important about writing allocation-free code? And I think one of the problems really is that working with C# is a very nice language to work with. The .NET Runtime is a very nice platform to work on. We've got used to having managed memory. And we get used to the runtime dealing with everything for us. We allocate stuff, it cleans it all up for us. We don't need to think about it. We've got this idea that managed memory is cheap. And that's not strictly true. Allocation is cheap, more or less. The runtime gets a big block of memory from the operating system. And within that, then, it manages the memory for us. And when we need to allocate something, it effectively just moves things on at the end and gives us a little block there. So allocation is nice and cheap. But garbage collection is expensive. We've got this block of memory. We want to sort of mark everything in there which is no longer being used as unused, and to clean it up, we have to work all the way through all that and then move it, compact everything down, and clean things up. So it's the garbage collection thing which is expensive. So we're not really talking in this particular instance about using too much memory, but it's about your memory throughput. And your memory throughput here, it means that your peak memory might actually be quite low. So you might not be sitting there at 4 gigabytes of address space full, wondering where all my memory has gone. You might be sitting there at something nice and low and reasonable. But over a period of time, your memory traffic, the amount of memory you have allocated and have cleaned up, could be absolutely huge. And this can this whole issue with throughput can cause problems for you. So the idea is more allocations mean more garbage collections. More garbage collections introduce in pauses into your code, and those pauses then disrupt throughput. So better throughput essentially gives you a smoother experience with your application there. This doesn't necessarily mean that things will be faster. They probably will be, but it might just be that things are smoother rather than spectacularly faster. But better throughput really is good for areas where you need to do things with which require a bit of low latency. So servers, if you want to try and get a very good response time out of a web server, for example, or a game. If you're writing a game, you don't want things to be stuttering. You want your frame rate to be good and quick. And similar sort of thing with interactive user interfaces as well. You don't want to be typing away in your editor, and all of a sudden a garbage collection kicks in, and you have to wait a second or two before you can carry on typing. Thank you. So it's good for a certain number of things there, but a lot of applications fit into those kind of things. And so this does work, and what I'm saying is don't do all these sort of micro-optimizations that we can talk about. This is still really useful things to be thinking about as you are writing your applications. It's also useful if you're ever working in a constrained environment, such as mobile devices, consoles, and so on, where you don't have as much memory as you would do on a big desktop machine or on a laptop. So generally speaking, using less memory is a good thing. So you want to reduce your allocations anyway. And if you're on a less powerful device as well, your garbage collections might actually be slower. So again, by reducing the number of allocations you have fewer garbage collections, and things can then be a whole lot smoother and quicker. And again, talking about throughput, if we're talking constrained environments, if we're talking mobile devices, mobile gaming is a big, huge business. So for example, Unity is a big deal on mobile space there. They have a statistic where 50% of the applications on mobile are written in Unity. And of course, Unity is a .NET environment. It's running on Mono, but it's still C#, it's Mono, it's the garbage collection, the garbage collector, managed memory, and so on. So these things are very important. And finally, another reason to do this is really to know your platform. So we work at different layers of abstraction, and I'm a big believer in the idea that you should know the layer below you're working at, so you can better understand the code that you're actually writing. And something interesting here as well is that even if you don't use it, you're still going to be using it. The things I'm talking about today, you're still going to be using it because the platform is using it. So if the platform's using it and you're getting a boost of performance just from the platform itself, it's useful to know what's happening and why it's happening and how it's happening. And I think it's useful to point out that performance is a key part of the design of the platform as well. So you can see this in things like C# recently had tuples added to it. And there's a perfectly good type there they could have used. They could have used system.tuple. It's been there for years. It's been in the base class library, but they didn't. They used system.valueTuple. And that's because system.tuple itself is a class. It's a reference type, and then you can allocate that, and it'll sit on your heap, and then it'll get garbage collected and so on. Whereas value types are implemented as structs and as value types, and that can then lead to less allocations and be a whole lot more useful. There's a similar thing with iAsync enumerator, which is going to be part of the await for each feature in C#'s 8. And what they're using there, that's going to be using tasks, but what it's actually going to be used there is value tasks. So again, it's something which doesn't necessarily require an allocation. And then, of course, we've got span of t, which is a very new type which has been introduced there and is a really interesting type for working with blocks of memory and for subsets of blocks of memories without allocations. So performance has really kind of been thought about as they're designing and building the platform. All right, so if we're going to talk about allocation free, it's not just allocation free, but it's also about reducing your allocations. So there's a bunch of things you can do here without having to work with some of the new things like the span of t and so on, which you can do to help reduce your allocations. So the simple one there, object reuse. If you've got a list or an array which you're going to be populating or anything, keep that around and pass it back in again. Use it, empty it, clear it, and reuse it. Same with objects. You can do object pooling, and you can do all those kinds of things. String concatenation is an obvious one, which is going to allocate stuff for you. There's types which can help with that. Obviously, string builder is going to be a good one for that. Parameters. Now, params arguments, this is an interesting one, because this is something whereby the compiler is going to be creating allocations for you, which you might not be aware of. So if you've got a params arguments-based method, like on the left there, passing in an array of strings, you want to be able to call it nice and conveniently with a set of values that are going on there. What you actually end up is the compiler allocating an array for you. And what's even more interesting is when you have an empty method call, it still generates an array for you. And it generates an empty array. And it'll allocate that every time you call it. So you need to be aware of these kinds of things when it's happening. And even more, you have to be careful of people telling you that, because that's not strictly true. It depends on which framework and which version of the compiler you're on, because the newer versions of the framework, newer versions of the compiler, will actually use the array.empty type, method, and that will then use a static instance, which is shared across different generic instances, instantiations of the types there. So what we get in a modern compiler and a modern version of the framework is no allocations going on there. So you kind of need to measure this. You need to know what's actually going on there. You can't just trust that somebody's telling you the truth and not trying to stitch you up on stage. Okay, another one which is useful as well is boxing. This one's a good one to understand. This is about the sort of reference types and value types again. And this is about passing a value type to a method which expects a reference type. This doesn't happen. So this doesn't work terribly well. And you have to sort of convert your value type into a reference type, and that allocates a new object on the heap, which contains a copy of the object. Right, hang on a minute. Let's do a bit of back to basics here. Reference types and value types. Everyone's heard about reference and value types? Excellent, very good. So the differences are really fairly sort of substantial. I mean, the first one is an easy one. You've got reference types defined by the keyword class and value types with the struct keyword. And one of the big differences is how they are allocated in dealing with memory. A reference type is allocated on the heap. So you've got a big area of memory to be used purely for allocating objects like this. And then you've got value types which are allocated on the stack. You can also embed a value type inside a reference type, which is fun. And so that means you get an actual copy of that data inside your reference object. So if you have a person object, for example, when it contains an int containing their age or their date of birth or whatever, then that is actually copied directly into the person object. Key difference is also how they are being used. So a variable for a reference type is a reference to the thing on the heap. So if you've got a variable, it's pointing, it's saying it's over there. That's where the thing is on the heap. Whereas a variable for a value type is the value itself. So this variable here now, it's just an integer. It's 42. It's the number. It's the value. And that then affects how things are passed around into methods. So if you've got a variable which is a reference saying it's over here, when you're calling a method, all you do is you pass that reference to the method. And now this method says, oh, it's this thing over here. It's pointing at the same thing. It's using the same thing. It knows how to do it. It's a reference. It says it's over here. However, with a value type, you pass a copy of it around. You pass it around by value. And so that means if you have the value 42, then this other method here gets a value 42. But it's a copy of the value. It's not the same value itself. So with integers, it doesn't necessarily matter. You're not going to change it. But with some other value types, so for example, a two-dimensional point of x and y, you might want to change one of the values, the x or the y value. But because you've got two different copies here, it's not going to affect the original one. And this is something which is very important, very useful to know and to know what the difference is. And this doesn't just affect passing things in to methods either. This also affects assignment. So if you make an assignment of a reference type, so person p1 equals p2, then that's just copying the reference. It's still pointing at the same item. Whereas if you have two-dimensional points, point 1 and point 2, if you assign that, that's a copy. And so again, you're not going to be able to change the original version by changing the copy. Does that kind of make sense so far? Excellent. Because I've also been talking about the heap versus the stack. And it's not necessarily very clear what that's all about as well. And so high-level view really is a heap is general purpose memory. You can just think of it as somewhere you can put your objects, and they just live. And the big difference really here is that this can last for the lifetime of the application. So you allocate something, it lives in the heap, and as long as something's using it, it can stay around for the lifetime of the application. Whereas the stack is a block of memory which is just for storing local data that is required by methods. And each method, when it's called, it pushes some space onto the stack. And it can then have all of its local variables inside that space there. And when that method finishes, it'll pop the stack, it'll clear that stack, it'll drop it back down to where it was before, and that space which was being used for local variables is gone. And so those local variables are gone. And this means that stack allocation is for the lifetime of a method. So we've got heap, which is the lifetime of potentially the application, or as long as you need it, whereas the stack is only just for method lifetime. When we create value types, they're created on the stack. And because value types are the actual whole data, that whole data lives directly on the stack. So if you want to put a two-dimensional point on the stack, it just lives there, straight on the stack. There's nothing going off to the heap or anywhere else. This means then that allocation is cheap, because it's just on the stack, it's right there. So we've already got that with the heap, that's fine. But cleanup is cheap as well, because we're just getting rid of the stack. But you are limited, because your lifetime of that object is limited. It's also worth pointing out the stack alloc keyword as well. This allows you to create blocks of memory on the stack as well. So if you wanted to normally create an array, that would go in the heap. But with stack alloc, you can actually create it on the stack and have a block of data there, which you can then clear up as the exit. So let's just check. So just to kind of recap then back on some of the boxing stuff, if you pass a value type to a method which expects a reference type, it's not going to work, because you've got these two sort of incompatible types going on here. So what you have to do is you have to convert your value type into a reference type, and you do that by creating a box, effectively. The runtime does this for you. it creates something in the object type. Because a value type can live directly inside the data for a reference type, it just gets copied straight over there. And so now the object, the method which expected an object, so for example, console write line here, that's expecting a string value or an object which you can call toString on. I'm passing an integer into that. An integer is trying to be converted into an object. It can't do it. It has to get boxed. It has to be put into something that can be used and can be passed around. The original value is now in a box. It can't be changed because it's a copy. If you change it, it doesn't affect the original value. OK, so let's have another couple of things then which might be causing allocations which you might not be aware of. Closures. We've got something like here, we've got a lambda going on with a method there. We're using the name value, which is being passed in as a parameter to the method there. When you write a lambda like this, which is using variables inside it, the compiler will rewrite that into a class. It'll pull that class out, it'll pull those variables out. Those variables become fields on the class, and it will allocate that class for you to capture that information. So there's an allocation going on there. You can see it here as we're being told the name parameter is being captured as part of this closure. This affects everywhere we're using closures, and one of the places that we use closures a lot is in link, where we're using our select, our where clauses, our first or default, and so on. And that can then have an effect on us. So if we're doing a lot of chained calls for linked, we're actually going to be making quite a few of these allocations. And even further then, link itself, the way it's implemented, a lot of the time it will allocate an object which will be the enumerator itself. So you'll have an object which is the enumerator, which will then keep a capture of this closure class, and you've got more allocations going on. So one of the nice things you can do, though, is here, and for example in the boxing example there, we can use some various plugins to show us these kind of things. So one of the guys on the ReSharper team wrote a plugin a while ago called the Heap allocation viewer. And this is really useful because it'll highlight where there are these kind of hidden allocations going on. These allocations which are not explicit. They're not there because you've called new, but they're being done behind the scenes for you. And these can then sort of inform you then when you've got allocations going on. You've got a sort of similar sort of thing with iterators as well. If you're using yield return, that gets rewritten into a state machine. There's an object which gets created and allocated for you. And also async await. It's even more sort of complicated there. Your code's rewritten into a state machine again, but you also get that state machine allocated plus also a task method builder and all the sort of accompanying infrastructure around that. That gets allocated. And when you are creating a task to return, whether it's a task or a task of T, that's going to get allocated as well. And so this can be expensive for some of the common use cases. So if you've just got a simple synchronous return, I'm calling an async method, but it's already got the value. I'm having to allocate an object just to return you an object that I've already got. So there can be an expensive thing going on there. Also, task of T, for example, has a lot of it has support for reuse. I can get my value out of my task again and again and again. It kind of caches things for us. And some of that infrastructure then has a cost. And so one of the things that has happened in recent releases is this value task type. And there's a nice link here which explains a whole lot about it. It's a value type, which kind of is a very lightweight version of task and task of T. And it's only really useful in certain scenarios, but it's in the most common sort of scenarios there. And so it's useful. This link here, I've got a slide at the end with some links there, so if you want to grab that later, that's no problem. But it's a really good article about how and when you should use value task. Right, let's have a look at something a little more fun and interesting. Reference semantics with value types, which is a big mouthful for a whole lot of nice little features which have been added in recent versions of C#7. So C#7 has had point releases, and 7.2 added a bunch of things which really gives us some nice stuff here. A couple of things were in C# 7.0, but most of this came in 7.2. We've got a few things. We've got ref locals and ref returns, ref read-only, read-only structs, ref structs, and in parameters. So that sounds great, doesn't it? But, you know, what am I talking about? What does this all actually sort of mean? And it's the idea that allocating a reference type, allocating and freeing and having managed memory here has a cost, so with a garbage collection and so on, but passing it around is cheap. It's nice and cheap to pass a reference to another object, and it's all pointing at the same object, and you can use it, and you can modify it, and it gets used. Whereas on the other hand, allocating a value type is cheap. It's cheaper to allocate and free a value type, but passing it around has a cost. You're paying for the copy, although that's not necessarily terribly expensive, but you also have the downside of not being able to modify that. So why can't we have the best of both worlds? And that's what reference semantics with value types allows us to do. So put simply, it allows value types to be used just like a reference type. We can pass it in, we can pass it by reference everywhere, and we can modify it, and Zadel modification will affect the original version as well. So this allows us to reduce allocations. It reduces the copies that we're making as the value types go around, and overall then it just reduces our memory traffic, and this is a good thing. So again, very low-level micro-optimizations. You probably won't want to do this, but in the times that you do want to do this, this will be really cool. And it's also going to be used in the platform, which is also very useful. It'll be used in the platform, it'll be used in games, it'll be used in parsing, in serialization, and so on. So this will probably mostly affect you by using libraries where other people have done this. But when you have a very critical hot path in your code, this might actually help you. Okay, but what does pass by reference and pass by value sort of mean? And again, it's the idea that a variable for a reference type is a reference to this object living on the heap, whereas the variable for the value type itself is the value. So a variable of an integer is the number 42, it's the value. Passing a reference type to a method is just passing the reference, so the method sees the same object, it's that object over there. If I modify that object over there, both the caller and the called object see the changes. Passing the value type to a method copies the value, and if you assign it to another value as well, then you also copy the value. The original value is unmodified, and it's also important to point out that the copies aren't actually that expensive. But if you're talking about micro-optimizations, if you're talking about these kinds of low-level optimizations, then they do start to add up. Okay, so the first feature that kind of works with this, it's all built on top of each other, and they sort of build up then to give you the full feature set, is the idea of ref return. This allows you to return a reference to a value type rather than a copy of it. Normally if you return back an integer or a two-dimensional point, you'll get a copy of that value. But here you can return now a reference to the value. So the return type of the method becomes a reference. So it's not just return value of int or of point to d, it's a reference to an int or a reference to a point to d. That introduces a constraint. The lifetime of that object, the returned value, it must exceed the lifetime of the called method. So I can't return a variable in the called method because a variable in the called method lives in that stack, but the method has just cleaned up the stack, and so it's gone. And so I can't have a reference to something that's just gone. So it's got to be something which lasts for longer. So this would be a field or a method argument because it got passed in. If it got passed in, it must exist outside the lifetime of that method. And so we have to use that. Modifying the reference is the same as modifying the original value because it's a reference, it's the actual thing itself. And you can do some really interesting things with that there. You can have a return reference to an array cell, so to an item with an array, and update that. And so you're actually updating the value in the array itself without touching the array, which is a bit weird, but cool. The way you use it is nice and easy. You just add the ref modifier to the declaration, to the method declaration's return type and to the return statement itself. And one thing that's important to point out is you can't use it on async methods because they get rewritten into a class and it gets pulled out, and then you can't sort of justify the lifetime anymore. But now that we're returning a reference, how do we use it? Because if I try and put a reference into a variable of an integer, that's an integer. So I can't put a reference into an integer, I need to put an integer into an integer. So how do we use it? And that's what the ref local feature is all about. If I'm returning a reference back, I need to have a reference to put it into. So if I tried to assign it to a non-reference type, it will create a copy of it, and that's not what we want. We want to use the whole reference. So ref local, it's a variable that is a reference to a value type, and accessing that will use the original value. And the key thing here as well is that if you're using var, don't get caught out by thinking that the type inferencing will work for you here, because the var will tell you what the value type is, but you still need the ref modifier. So we'd use ref var to be able to use type inferencing. All right, so let's have a quick look at some code. So I have a point class here, which has got an x and y values there. I'm creating it with a constructor. And I have an enemy class as well, which takes in a point as a constructor value, and I can get the location, which will just return it back, or I can use this get location by ref. That's got the ref keyword as part of the declaration and as part of the return statement as well. And we have some tests now which will sort of then verify behavior. So if I create a new value here, which is going to be an enemy at point 1010, I can get the location, I can set it to be 12, and I can confirm that it has actually worked on that location. But if I get it back now, we can actually see that my expected value is 10 because it hasn't changed anything because it's a copy. So if we just quickly run that one. Tell you what, let's clear all those because I can't see which one just ran. If I could press the right keyboard shortcut. Gesundheit. Okay, let's try that again. Run that one. We see the one test that we've got, and it's green. So it worked with a copy because I was pulling back. I wasn't doing it by reference. So in the next test, then I'm doing get location by ref. This is going to return me back my value using return ref here. But I'm going to put it into another point, which is a value type, and so it's actually going to be a copy. And I can confirm that again if I change it and then get the value back again, it's still 10. If I use ref var here, I can change the value then, and my expected value tells me it should be 12, it should be changed. And if we run that one, we've got green and everything's good. So we know when we're working with copies and when we're working with the actual reference. But you can do something weird as well, which is fun. So you can have a method as the left-hand side of a call there. So we can have enemy.getLocation by ref as a method as the left-hand side of a thing and assign a new point to it, which is bonkers. Because it's returning back a reference to the field, what we're doing is we're assigning a new value directly to that field. And so that one's changed there. And so where previously it was 1010, it's now 4242 because we've just overwritten that field because it was a reference. Does that make sense? Good. That one hurts my head, that one does. It's like method on the left-hand side. It's just strange. Okay, next one then is in parameters. This is an argument to method parameters. No, sorry, a modifier to method arguments. It was written right there. And this kind of complements the out and ref keywords as well. So you've got an in keyword. This allows you to pass things in by reference, but the method is not allowed to modify the original value. So whereas a ref passes something in and gets it out just gets a value out, in just gets a value in by reference. But there's a problem. The idea is that the method can't modify the original value, but there's no way for the compiler to enforce that. Because the compiler, or rather, there's no way for the compiler to know that, because any property or method on a struct can change its own state. And if it changed its own state, it would come back and it would have changed, and that's not good because the whole point was it's an in parameter and you shouldn't be able to change it. So the compiler enforces safety. It makes a defensive copy when you're calling a member. We can have a look at that as well. So if we have some in parameters here, I've got a mutable point. So I've got x and y values here, and yes, they're public fields, so anybody could change them anyway, but we'll ignore that. We've got a constructor, which is setting things up, and I've got a translate in place, which is just doing a simple translate, moving my x and y coordinates that are going on there. And I can run this calling methods here, and we can see that this works. Where are we? Let's show in parameters there. So everything works okay. I can pass in 10, and I can translate it in place, and it all works, and it's all good. Now, if I uncomment this, now this should be fine. Let's uncheck that one as well. We've got a test here where I'm trying to modify the in parameter. So I create a new point at 1010. I pass it into a method where it's got an in parameter marked on there, and then I try and assert that it's not being changed. And in here I try and change it, but the compiler says you can't change this. You can't access these values here. I can't modify a struct member on my public field because it's not classed as a variable, because it's an in parameter. You're not allowed to change it. But I can still call translate in place. And when I do that, I will get a copy of it, and it won't change. I'll get my defensive copy. So let me just undo my code which doesn't compile. And then we have another test here then which will do that then. It will call translate in place on an in parameter there, and it will wake up in a sec. It will die on me. Typical. Boo. Right, we close and reopen the solution. So yeah, so this one will create a new instance. It will call the do translate on with a variable, with an argument which has got the in modifier, and we will then see that it's called on a defensive copy, and we will see that translate didn't work. Am I actually going to have to kill everything? Yeah. Let's kill that. Right, we'll just pretend that test worked, and we'll move on to the next slide. Okay, so things are good there. We've got some immutability going on, but we've still got copies and things happening. And so we can pass things around by reference, but we've still got copies, and we want to reduce that. That's the whole point, that we don't want these. So we've got another feature then, which is the ref read-only return. And this extends ref returns and ref locals by telling us that we can't modify it. So this is an interesting one here, because we're returning a value by reference, but the caller is not allowed to modify it. So we can assign to a ref variable here, and the compiler enforces read-only again with more errors, and with errors this time, and also defensive copies. So for example, here we've got a point which we've defined as a static field there, a point of origin of 000, and I'm returning that as a reference. If I was returning it as a reference, somebody could change my origin, and that would be really bad for any kind of game I was trying to write. And so what we can do is say it's a ref read-only. Now, if I try and assign that to a variable, to a var, then I would get a copy of it, and it would work like that. If I try to assign it to a read-only var, then I will get a reference to it, but when I'm making invocations there, we will get copies being made. Now, just keeping an eye on time. I'm going to move on without demos on this one. We'll quickly look at read-only struct. This is then sort of like the next level on again. So it's an in parameters, and ref read-only can still create defensive copies because the compiler doesn't know that the structs methods will modify state. So then C# 7.2 introduced a read-only struct instead. So you mark a struct as read-only. You then have to mark all of your fields in there as being read-only as well. And so you get an immutable struct. And then the compiler knows that it can't change anything, that your methods can't change anything because all of your fields are read-only. And so you know it's immutable in its state, it's there, and again, no copies get made. And so again, micro-optimization, but we're missing out on copies. Key thing with all of this is there's no changes to the CLR, so that's a good thing. It's just all in the code and all in the compiler. And then C# 7.2 added an extra thing, which is a ref struct. And to be perfectly honest, I don't know why it's called a ref struct, but this is a type which can only be allocated on the stack. So this is a struct which can only live on the stack. So it can never be part of a reference type. So I couldn't have a person containing a ref struct because I could never have a person class containing a ref struct because that would not live on the stack. So this constrains the lifetime to the calling method. It also means that it can't be boxed, it can't be used inside a non-ref struct, it can't be used with async methods or instances, and it can't, because they get rewritten into classes, and can't be used as a generic parameter either. This then has very limited use cases, but they're very cool. So the first one is working with stack alloc memory, and the second then is span of t, which is a really cool type, which is all about working, unifying the way we work with a big block of memory. So you can work with things like arrays or array segments, strings and substrings, native memory, stack allocated memory, all in the same sort of manner. Basically, you get a lot of, it looks like an array, but for lots of different types of backing memory. So you have an array-like API, you have an indexer, and so you can do your item there, square brackets 12, and get at the value that's in there, or set the value that's there. There's also a read-only span, which provides just a getter, and so you can't modify the values that are underneath it, but it's there. It's also type safe. Each element is a type T. You can get a hold of it, you just work with it just as normal. So it is very much like an array, and it has array-like performance. So it's not quite as performant. Newer runtimes have special support for it, which make it basically the same as arrays, but that's it, and they're good. And the key thing, the really useful thing with it is slicing. You can create a new span which is based on a subsection of an existing span. So you can then say that my span is this block of memory here, and you can create a new span which is based on that block of memory there, and you don't have to make a copy of it. So it's using the same memory. The way it's implemented is that it's a value type. So again, no copies going around anywhere. You need to bring in the system.memory NuGet package. It's built into .NET Core 2.1, but the package will then give you sort of reference types for different frameworks that are there. It supports the .NET standard 1.1 and above. So it works on .NET Framework 4.5 and above. But the newer versions of the of .NET Core have support directly in the runtime for it. There's also new APIs and overloads in the base class library. Some of these would be part of the next version of the .NET standard. So things like read async, try parse will be able to return you back a span. This is really good if you're writing a parser, because then you can read a line of text and then split it up into little strings without having to allocate new strings. There are two different versions. So if we're talking about this, we're talking about performance. There's two different versions. There's a portable version and a fast version. The fast version requires runtime support, and this is in .NET Core 2.1 and above. I think it's 2.1, maybe 2.0. I've suddenly confused myself. I think it's 2.1. The portable version works on .NET Standard 1.1 and above, which is .NET Framework 4.5. It's important to say the portable version is not slow. It's not as fast as the fast version, but it's not slow. It's also not as fast as arrays. The way it works is by holding the object that you're working with, an offset into that object, and then the length, so you can get that item there. Whereas the fast version requires runtime support. The way it works is it holds an internal pointer. So if we've got the object here, it holds an internal pointer and the length. And so it's slightly smaller, and accessing a particular element is slightly simpler. But more importantly, the runtime has specific JIT optimizations here. So it can ignore the bounds check in a loop, just like it does with arrays. And so you get very, very close to array-like performances. So what does this have to do with ref struct? And the big thing is it is a ref struct. The problem is, for thread safety, you need to update all of these fields inside a span of T atomically. You can't do it sort of, you can't have one part of the pointer different and then change the length at a different time. You've got to have it done at the same time, and because the whole point of this is performance, you can't do that with standard locking synchronization. It's also the case that the internal pointers that the fast version use are quite expensive, so you don't want to have too many of those happening at any one time. We want to deal with lots of blocks of memory, lots of different types of memory, such as stack alloc. But if it's a stack allocated thing, how do you deal with that if your span is living on the heap? The stack can disappear at any time, and all of a sudden this span is somehow invalid, but you can't track that and stuff. So you make span of t a ref struct. It can only be created on the stack. It's got a constrained lifetime and single-threaded access, because the stack only belongs to one thread. Okay. I think I've run out of time for my demo. Sadly, I can do a quick demo. Right, I'm going to do this very quickly in a minute or two. So we've got a test here. Span does not allocate. I'm using .memory unit here, which is a unit testing framework for tracking memory usage. You create a checkpoint here, and we'll use that later. We create a string. We convert it into a span, and we say we can get a subspan of that, which is going to be between indexes 0 and 5. And we can even slice that span as well to get it between 0 and 5. And then we can do a bunch of asserts. We can assert that it starts with a particular string, that it's of a length of a particular length, and we can do a whole bunch of asserts there. And at the very end, we can assert that there are 0 objects allocated. That uses the .memory unit API to check to see whether any items are allocated. And then very simply, we can run that. Oops, I ran it incorrectly. So if I just run my tests under .memory unit, the profiler has to be running to run these tests, and so the chicken and egg scenario there, you can't start the profiler after you've started running the tests, so you have to run the test first. And we've got a first test there, which is actually showing that we've got an object allocation with a string, but then we've got a second one there showing we can do all that stuff with spans. We can create subspans. We can say we compare different strings and string lengths there without allocating anything. So apologies for the rush demo there. And so that brings me to the end. And here's some very useful links then on some of these kinds of things. The documentation for reference semantics with value types is very useful. It explains a whole lot of this kind of stuff. The good Channel 9 video with Jared Parsons, where he's explaining what span of t does. Adam Sitnick also has a very good blog post, again, sort of covering all this information there. There's details of some of the optimizations in the JIT, which are based on how span works. And then the last one there is the link from earlier on, which is Stephen Taub explaining the all about value task and how and when you should be using it. So that brings me to the end. 2 minutes over, apologies. Thank you very much.